So sponsorships tonight.
Well, thank you to Computer Futures.
Wait a second. We're going to come up and say something. So, wait a second.
All right.
We have 3 sponsorships tonight. We have Computer Futures, who are going to come up and say something in a moment. We have GitHub. Everybody, I don't know who they are. And we have Imaginary Landscape, which is an old school web weaving company. And we have someone that's Joe's gonna speak a little bit about that. So first, making this possible tonight, huge turnout. Give a warm thank you and come on up here, Computer Futures, please. Thanks, guys. And we're doing more with these guys, more and more, so we've deemed them not douchey.
But don't speak too soon.
No, give me that.
Thanks, Brian. I'll keep it short, but hey guys, I'm Charlie and this is Tom. We're with Computer Futures. Thanks so much for allowing us to to host the event and sponsor and all that. Just a bit of background on who we are. Computer Futures is a recruiting and staffing firm, so we focus on the IT space. The reason why we wanted to partner with people can hear me. The reason why we wanted to partner with Chippy is because we have specific teams of people that focus specifically on the Python space. We're really bought into Python. We think it's an awesome language, and we think it's only going to be kind of going up from here. And we think Chippy does a lot of really cool stuff. So we have teams that focus on Python within the finance space, and that brand's called Huxley. That was we worked with people like Jerry to help him get his job at Bank of America, and then we have a brand called Computer Futures, which focuses on the non-finance space. So yeah, we're super excited to be partnered with Chippy, and like Brian said, hope to continue the partnership and do some more stuff. And we're super excited about tonight, and hope everyone has a great time.
Thanks. Joe. So Imaginary Landscape, long legacy in Chippy and in Python community. Name a few when you give your intro of people who can do that.
I'm Joe Jasinski.
I'm here for the Go talk.
You got it.
I'm Joe Jasinski. I'm with Imaginary Landscape. We're a Django Python web developer here in Chicago. I've been doing it since 2006 and Python since about 99. Sure. We've had people come through us like Ian Dicking and Chris Weber and a bunch of others, Tomas. So we really love Django, and we work with a lot of cool web dev stuff. If you want to learn a little bit more about us, I'd be glad to talk about it. So come see me, and we're happy to sponsor, help sponsor Chippy tonight. So
awesome. Thank you, Joe. So I don't think GitHub's here tonight, but thank you to them too. So we're gonna get this started, and one thing is if you are not from the Python community, we've killed trees for this. So Carl has a lot of dead trees that have been mashed and tattooed with ink. So if you want to learn about how awesome Python is, I'm going to leave this right up here. So during one of our breaks, you can look at it, and he has more that he can give you, so you can put it on your fridge, if you so desire. All right, so we do have talks lined up tonight, and I'm going to tell you how this works. We're getting 7 minutes. Yes, I've increased it by 2 minutes per talk.
Thank you.
Because a couple of people, I don't know what happened, bad stuff happened, and they're not going to be able to make it. But there's plenty here. So we have 7 minutes. It is going to be timed. At the end of 7 minutes, you must stop talking. And you will stop talking, because I'm going to turn off your mic, and I'm going to wrestle. Jerry's going to wrestle you. He's much bigger. In a kind and soft manner, of course. And so the rule is there needs to be at least one Python reference. And you can just say the word. You can say, like, I like Monty Python Flying Circus, like a Brian. You can say, just say that, but you have to at least make one reference throughout the talk, because we are a Python user group. So there's going to be a break between sessions, and we won't start until someone gets ready. I'm going to put a timer on the desk. So we're going to go in the order of the people checked in tonight. So being on time always helps.
My name is James Swain. I work at Braintree with Adam Forsyth, and tonight Oh, sorry. Yeah. And tonight I'm going to talk about OCaml. The kind of phrase I think best encapsulates OCaml is that it's multi-paradigm. You can use it. You can write code using a lot of different programming styles, some of which are familiar to you, and others which may or may not be familiar to you. Kind of the predominant paradigm that you see in OCaml code is the functional paradigm. Some of you are maybe familiar with this, some of you may not. So this code sample here, this is just like an implementation of the map function, which you probably have seen. If not, it just takes a function and a list as input, and then returns to you a list that contains all the elements of the input list with the function applied to each one. So here you can see a couple of things that are sort of functional in nature. You can write recursive functions. You can do pattern matching, which is like a destructive sort of case dispatch on values. So here in match, the base case is do we get the empty list? So in that case, we return the empty list. Otherwise, if the list is an element cons onto a tail list, then we return the result of applying x to f cons onto map of the rest of the list. And then also here is another kind of, can everybody hear me? Okay, good, okay. Another example, or kind of example here, we're going to use the map function and we're going to create a list of the numbers 1, 2, 3, 4, and we're going to pipe it into map. And the map, that expression there is a partial application of map, where the function argument is adding a function that adds 1 to any number. And so here we're actually partially applying plus. And so that will give us the list 2, 3, 4, 5. Then we pipe that into filter, which we only return all the even elements in the list, which gives us 2 and 4. Also, you can do like actual object-oriented programming in OCaml. It's not as commonly used, but you have all the facilities that you would see in any language that has more emphasis on this sort of thing, like a Python or Ruby. And here, this is just like a basic stack class. Notice that also you can have like fields and methods, but if you want to do any kind of mutation, you have to be explicit about it. In OCaml, everything is immutable by default. And then also the thing that sort of comes along with that is the imperative programming style, where here we're actually using the stack class that we just saw in the last example, and we're actually writing just a basic for loop that you'd see in any language, C or whatever. And here we're just going to push the numbers from 0 to 5 onto the stack, and then pop the last one, we get 5 back. So quickly, since we're short on time, features that
4 minutes.
4 minutes, good, awesome. 4 minutes left, or
4 minutes left.
okay, cool. So some things that we've already seen, some things we haven't. OCaml supports it has first-class functions, higher order functions like a map or whatever. Lexical closures where you can create a function sort of inline that implicitly captures all the bindings that were outside the scope of the body of the function. It has static type checking with type inference. So you notice that in all of these examples, we never have any sort of type annotations anywhere. The compiler just kind of figures out what the type should be. And in some cases, you may need to use type annotations to kind of help the compiler understand what you're doing. Also pattern matching, which we saw. First-class higher-order modules, which is like a really cool feature that you don't see in a lot of other languages. You can write modules in OCaml that take other modules as parameters. You can write functions that build up modules using arbitrary values, functions that take them as arguments. You can do really cool stuff with that. There is a macro system. It's not quite as refined as like a Scheme or Racket or whatever. It's portable, it's cross-platform, just like Python. And it's actually very fast compared to like other languages in this family like Haskell or even Scala. It's got pretty good performance characteristics. It has some of the nice conveniences that you would see in other languages. It has a package manager. It's very actively contributed to. It's very easy to use. So this is just a screenshot that I took from the OPAM website, which is the OCaml package manager. It's pretty active, as you can see. There are 887 packages there now. This past week, there were like 27,000 something package downloads. So it's got a pretty active community. Notable users. This language is actually used like in real life, which is kind of cool. So Jane Street Capital is like the biggest, probably commercial user of OCaml in the world. They do like quantitative trading, high frequency trading. They're based in New York City. They write their whole stack. Their whole stack is in OCaml. They have actually like rewritten the OCaml standard library and like improved it. So they've rolled like their own sort of like OCaml ecosystem. They have a lot of nice build tools and stuff. So it's pretty neat. Bloomberg apparently uses it for some of their like pricing tools that I know very little about. Mirage OS or Unikernel, which is actually a really nice project. So you, as I understand it, you can write OCaml programs and then compile them into like virtual machine guests that actually run directly on like a Zen hypervisor, and they're almost exclusively written in OCaml. It's very cool stuff. Okay, and then the Facebook hack language. I don't know if you're familiar with that. It's like a PHP-ish language, I think. They wrote the compiler in OCaml, and then INRIA, which is like it's a research organization in France, which is basically where OCaml was kind of invented. So they're heavy users of it, obviously. So that's it. You can get OCaml at that URL. You can try it in the browser also. And if you don't believe me that it's actually a nice language, I recommend that you read this article, which is a really nice sort of point-by-point list of why it's a nice language. You should use it. So that's it.
Everyone, I'm Feihan Xu, and this talk is pretty much what no false advertising, so I'm timing myself to stay within 5 minutes. But I'll like 5 minutes, and then maybe questions, or just random gibberish. I can do that for 2 minutes, I think. So this is gonna be, well, it's a little weird, but whatever. Just it's going to be weird, whatever. Okay, so I think everyone knows what Swift is. I mean, raise your hand if you don't know what Swift is, right? Everyone's heard of Really? What?
Sorry,
Okay, so it's a new programming language. It was invented by Apple, introduced in 2014, last year, and it's designed to be a replacement for Objective-C, which is this terrible language from the 80s that is still around because people like iPhones. Okay, so so you might be thinking, why should I care about Swift? And that's a good question because it's sort of a very limited language because it only works on 2 operating systems, basically. Like I said, it's a very decrepit 80s language that they bolted a whole lot of features on top of to make it more relevant, but it still hasn't addressed like the fundamental problems of it. And then, when people talk about Swift, they don't use the word monad, so obviously it's not a cool language, right? It's not a hipster language. In fact, all the ideas in Swift that are good, they have already been fairly thoroughly explored by languages like Haskell, Rust, Go, like whatever, probably all the other languages that people are talking about. Oh, OCaml, I'm sure, right? So if I were so bold as to make an analogy, I would say that Swift is like an uncool uncle. Okay, so it's not the opposite of a cool uncle. Okay, so it's an uncool uncle is an uncle of yours, is a relation who is not explicitly lame, but really not particularly cool. Okay, and I'll elaborate. Hopefully this analogy will make sense, but I don't really guarantee it. So. Here is like a hypothetical uncool uncle named Uncle Swift. So these are the things that he's into. So his favorite rapper is Eminem, who's also the only rapper he knows. His favorite movie is the original Men in Black, and he thinks the best version of the X-Men is the one from the 90s Fox cartoon. So these are his favorite things. And these things are not bad. I'm not like making fun of these things. Like they're just not as cool as they used to be. And then, but on the other hand, just because Uncle Swift is not inherently cool does not mean he's not interesting. So let's say that he used to fly planes in the military, and then he switched to commercial aviation. So now he's flying like Boeing, the Dreamliner. I don't know, is that a 767? I don't remember. 787, right? And so like that's cool because everyone's we've all flown before, probably, right? We've been inside of a plane, but he's the guy who gets to be in the cockpit, and so that's kind of cool. And so in that same sense, Swift can be interesting because of its execution context, because not every language gets to run in your mobile phone. In fact, very few languages are able to do that. So like one of our favorite language, hopefully our favorite language, doesn't really get to do that, with like a very small exception. I know there's a thing called
favorite language?
Python. I was gonna save. Don't worry. So so Python can run on iOS through this framework called Kivy, which you might have heard of before, but it's geared more towards games and media applications, and not so much like normal applications that you usually use. And well, I guess I will go to 7 minutes. So Uncle Swift, though, he's definitely cooler than Grandpappy Objective-C, because those are things that he's into. And so I don't think I need to explain that. So, but Swift has some interesting features. It has a REPL, a read, eval, print loop, and also you can run programs in it without compilation, which are usually things that you only see in dynamic languages. And so, but you might ask yourself, like, why is that in there? Like, why do you need like these dynamic features? Well, one of the reasons is that when you're writing a fairly large program, you often want to just run like a small part of it, because it's going to have a lot of parts. So a good example is when you're doing UI programming, which is what is the focus of most Swift code, which is for iOS, is you have a view that's like deeply embedded in your navigation flow, and you don't want to have to run the entire program just to like work on that specific view. So this is actually a very valuable thing, because it's a common pattern of program design and how you work on stuff. So I don't know how deep we're going to get because I only have 2 minutes. But so here's the REPL.
30 seconds.
Okay, so here's the REPL. It works. It's just basically a Swift command. It's okay, basically. And basically you just run it like that, and it's very simple. But there are a lot of problems with it. There's no -i option like you have in Python, so you can't bust into interactive mode after you've run the program. You can't import other Swift files. You can't debug. Basically, it's basically kind of shitty. And then there's another thing called playgrounds, which you might have heard about. They're essentially like Swift's version of IPython Notebook. And so if you look at the screenshot, yeah, it kind of looks like IPython Notebook. You can render stuff, and the code is sort of run inline. You can see the results kind of on the right side if you can squint that well. And then it has some really nice things about it, which I'll just let you read. And then, but it has like a whole bunch of bad stuff. Like it has a lot of the same problems as the REPL. It doesn't work super well yet, and for the common case of rendering interactive UI, it basically just doesn't do anything. Okay, and then it also has type inference. I'm gonna skip this, and then that's pretty good, but it sort of doesn't work so well. And then it also, okay, that's the recap. Just read that. And then you might ask yourself, is Swift worth learning? Well, maybe, because Uncle Swift, like, let's see you run into him at the family reunion, and he's got some cool stories, and he's definitely, his stories are better than a certain someone's stories, and he might, as he gets more drunk, he'll get better over time. And I think Swift, you have that same kind of phenomenon where there are problems right now, but hopefully it'll get better. And I'm going to stop. Thanks.
Thank you.
All right, I'm ready to go. Give me the.
Just nod, ready?
Nod.
All right, go.
Python and R. Let's go. All right. This is my. Well, I have a few pictures, but this was a very good time. This was PyCon. I encourage everybody to go to PyCon. It's in Portland next year. You get to learn a lot. You get to go out with a lot of cool people, and you get to have some drinks and socialize. Now, my job, I was actually sent to London exactly, a couple days after this. I had to go straight from PyCon to London. I had a lot of work to do. But what did I do? I had some drinks. I don't even know what this picture was.
You wear your sunglasses at night?
Yes, that's an 80s reference. I'm like Uncle Swift, so apparently that's me. Although, in my defense, I stopped the bar fight 20 minutes after that. So, okay, I was wondering, should I be worried, all right? So I'm supposed to be doing a lot of work. I did, but I was also having a good time. How can I analyze this? So since I'm a technical person, I go, I'm going to do some regression. I'm going to say, you know what? I want to see like if people make good decisions after they have more drinks. So let's do some regressions. What is a regression? Regression is a very complicated topic, but at the end of the day, it's a best fit of a line through a plot of data. So you get a bunch of data like this, and this I couldn't find a better slide for this, but you have quality and price. Quality in this case is the independent variable. Price would be the dependent variable. And you want to basically move quality around and see what happens with price. Now you can kind of see what's going to happen here, and you get a best line of fit. What this allows you to do is use quality as a predictor of price. Now, can I find some data to say if I shouldn't be getting pictures like that from people in London? I couldn't find any good data samples on alcohol, but I could find some on college. I've got a lot of boys, and they're getting ready to go to college, and it's going to cost a lot of money. So we have to make some smart investment decisions. Now, what I'm going to do right now, how much time do I got left?
You got 4 minutes and 30 seconds.
All right, actually, not bad. All right, I'm going to go in demo mode. And Sean and Catherine, I'm going to break some of your rules. I'm sorry. This is R, it's a good language.
Ooh.
All right, my simple 4-step process was this, okay? I want to get a file from the internet, put it into a data frame. Data frame is the basis of the R programming language. I want to run a regression on it, on the data frame, and I want to display the data. Simple 4-step process. The only thing out of the box with R that I had to install that just didn't run, I'm using RStudio, by the way, it's a very good IDE if you're doing R, is I had to use install packages because I had to read Excel data. Install packages is like using pip. So you think Python, pip, install packages R. Require, that's a line that says, that's a line that's like an import. So 4-step process. Download the file, which I did once. I'm not going to do it again. And then you'll read the file into a data frame, run the regression, plot the data. And I'm doing ACT versus graduation rate. Okay, Captain Obvious, surprise, surprise. In the 1993 data plot that we got of all reporting colleges, when they reported the average ACT score, when you compared that to the graduation rate, you see that the higher your ACT, the school with the higher ACTs had a higher graduation rate. So that was pretty straightforward. It's like 14 lines of executable code, and it was very quick to do. Now I'm going to How much time, Brian?
2 minutes.
I'm going to demo Python. I guess I'm going to have to speed it up a little bit. Okay, Python is our favorite language. It's general out of the box. I used virtual env, and I wanted to use, I wanted to do a sample regression. I used the stats models package. From there, you have to install things like pandas. You have to install NumPy, and a lot of other things that are pretty automatic to come with it. If you look through that list, XLRD was for the Excel piece, and I used requests when I downloaded the data off the internet. It's all in, you see ZStats1, that's my virtual env environment. I'm using PyCharm, don't hate me. Same thing, same simple 4-step process. This is all the Python we know and know and love. Step 1, get the file, read the file. What the fuck? Oh, sorry. Run the regression and display the data. very much the same thing, it's just slightly different. Step 2.5 was this Patsy package that comes with stat models. Couldn't accept space in line 20. Couldn't accept the space in the regression equation. $30 seconds. Uh-oh, I'm running out of time here. Oh, okay, it's not going to run, so that's nice. R wins, ease of use, Python wins there, and in the end, Python wins.
Very good, very good.
All right, well, hello, everybody. Thank you for coming here tonight. We were asked to pick a language and compare it to Python, giving you a chance to vote on your favorite presentation. And we need to do this in 5 minutes, so let's get started. The language I picked is QML, and I said, if you think Python is Pythonic, wait until you see QML from the point of view of an experienced Python developer. Now, Python, of course, is the general purpose programming language that we all know and love. Okay, sorry about that. And the notion of being Pythonic is pretty well captured in the Zen of Python by Tim Peters, otherwise known as Import This. However, if you want to create a graphical user interface for your application, you won't find what you need in the Python standard library. And that's where something like QML comes in. QML is primarily for creating user interfaces by declaring a hierarchy of visual objects and their properties. And while there isn't yet a Zen of QML, there is something about QML that, at least to me, feels rather Pythonic. So let's take a look at some QML code. Well, every graphical user interface needs a window, and this is how you declare one in QML. So imagine a very simple text file named example.qml with the code you see here. When this is executed by the QML engine, you get a window like the following. And it's just has a title and is resizable. It's simple, but it's pretty boring. And oh, got ahead of myself. So let me explain really briefly here. So what you see in the first 2 lines of code are some input statements. They're similar to Python, but a little bit different. And they set up the QML environment and allow us to declare objects. A window is a built-in object type, and we can declare a window object instance by typing its name, window, followed by some curly braces. And within those curly braces, we can assign property values, which we've done here for the width, height, and title, and that's how you see the window that I showed earlier here. Like I said, this is pretty boring, and QML itself is anything but boring. It's got powerful features like property bindings and a great signal and event handler system, and it even allows scripting in JavaScript. So in this second example here, we've changed the title and introduced a text object. And when that runs, you see this window here. And I don't know how well you can see the title there. But the window title is no longer a static string value. Instead, what we have here is a JavaScript expression. And it's concatenating a couple of text items together with value X and Y, which happen to be properties of the window object. And whenever the QML engine detects a dependency within a property binding, such as this, the dependency that title now has on the values x and y, it automatically reevaluates the expression anytime one of those dependent values changes, which automatically changes or updates the property. And you can see that as we move the window around, the window title is changing for the x and y origin point. Likewise, the text value is automatically changing its size, position, color, and value, all automatically thanks to property bindings and JavaScript expressions. For example, the font pixel size height here is always going to be 1/4 of the parent's window's height. In this third example, got another window here, and we've introduced a mouse area object that fills the entire window using anchors, which is a layout feature. When we click on it, QML emits a clicked signal, which we can handle in the onClicked handler for the mouse area. And there we have some JavaScript that sets the text object's color to a random color provided by a function that we've defined up here within the window object, which returns a random color. Now we're able to reference the window object and the text object through their ID values, window and some text. Every time the color of some text changes, we increment a counter in the onColorChanged handler. The counter that we increment is an integer property that we have added to the SumText object, finding it here. So QML automatically provides these onPropertyNameChanged handlers for all object properties, even user-defined properties. So we even have an onCountChanged handler for our user-defined count property that we've added. 1 minute, let's see. Oh, it's covering up my, oh no, yeah. Oh, I'm over 1 minute.
Yeah, we have 7 minutes. So.
I'm almost done. So that's where we update the text value when the count is greater than 10, which if we get to 10, we see that the text changes. So with all these features that QML provides, surely someone would use QML to create a slideshow presentation system, one where you could even have an old school game of life simulation running inside one of your slides, or even a fancy color one. Maybe I should have named this presentation QML versus PowerPoint. Indeed, this presentation was written in QML using QML Slideshow, and all of the code is available on GitHub. Thank you.
All right, so I'm going to talk about PostScript. And in honor of Chippy, and because PostScript is designed to draw things, I drew the Chicago flag as a demo instead of a hello world. Let's see. I'm going to come back to this at the end. And my first idea for this was to step through this code and explain the code as we go. But I realized it's probably better to start at the beginning and just give you some background on the language and then maybe come to this at the end, but it probably won't have time. But I did write the PostScript here on the left, and I translated into Python style syntax so you can figure out what's happening. But I'll come back to this at the end. I just want to give you a sense of what PostScript is for, and it's for drawing and stuff like that. So, the first thing to know about PostScript is, yes, it's a programming language. If you're familiar at all with PostScript but don't know much about it, you might have seen it as in the context of like documents, or think of it as a file format. Like here's a Mac. If you double click on this hello.ps, it opens up preview just like it would open up any document. So and there's hello.ps.gz is zipped PostScript, and there's something called encapsulated PostScript .eps files you might have seen, and those are often treated like images. And they are sort of images, but inside all these files, you open up in a text editor, it's PostScript code. Okay, so that's why it's sometimes called a page description language, and its goal is to generate vector graphics. And one of its biggest uses is in printers. So a lot of printers, I don't know current status, but it was certainly developed with printers in mind, so that printers natively understood PostScript. You could send it PostScript and it would print those documents. All right, so here's just some basic facts about PostScript. It's a stack-based language, which I'll explain a little bit more in a minute. It's interpreted. It's dynamically typed. It has a very minimal syntax. It has a REPL, garbage collection. I've listed here all the built-in types. If you can see that, most of them are pretty familiar to Python people. Strings, arrays, dictionaries work a lot like Python objects. There's some other kind of weird ones there. But I highlighted the ones that are basically common with Python. So it's surprisingly close to Python in some ways, and other ways very different than Python. So one way that is different is it uses postfix notation. So let's say you have a binary operator plus. It takes two arguments, A and B. There's basically three ways you could write this. A plus AB, A plus B, or AB plus, right? And these are called prefix, infix, and postfix. Postfix is also known as reverse Polish notation. If you've heard of that, there's some well-known calculators from the 70s and 80s by Hewlett-Packard that use RPN, and PostScript is actually a lot like those calculators. Yeah, so for better or worse. So why is it? So I mean, in my opinion, I think postfix is the most unnatural out of these three in terms of thinking about addition. So why does it use that? Well, it's because it's a stack-based language. And maybe a lot of you have heard of stacks, but that's like a basic data structure that has basically access to a list of items only through the top item. So you push things on the top, or you can pop them off. That's it. It's like a stack of plates in a cafeteria, basically. And everything in PostScript, function calls, use this stack to handle the operands, and I'm going to show you an example of that. So this big text here, 27 add, that's a little snippet of PostScript code. So it's 3 tokens, 2, 7, and add. All right, so you see it's a PostScript postfix notation, right? Add is at the end. The arguments are at the beginning. So if you step through like the interpreter would, basically when it reaches a constant or a literal, in this case like an integer, it just pushes it on the stack. All right, this is the interpreter too. This is in parsing. This is actually as it's running. It reaches a 7, same as 2, pushes it on the stack. And I've drawn this kind of like a Python array. So the top is on the right. So when it reaches this word add, it looks up in its kind of internal dictionaries and realizes that add is a operator, and it calls that operator. And internal to that, like it's basically like a function, it gets its arguments from the stack. So add internally says, I need to add 2 things, I pop them off the stack. And the result gets pushed on the stack. So after you do add, the stack now says 9. Okay. So everything works like that. Like all function calls, read from the stack and then push from the stack when you're done. 1 minute 30. 1 minute 30? Okay. Not probably going to finish, but this is an example from that flag demo that I have that's a little more involved. So in like Python, you write sdist equals width minus 20 divided by num star plus 1. So this is figuring out the distance between stars on that flag. In PostScript, you write this: sdist width 20 sub num star 1 add div def. Okay. It looks kind of weird, but once you start to think in this backwards way, like width 20 sub is width minus 20, and num star 1 add is num star plus 1. Div divides that result. Def defines it to this first thing, which is a name. So yeah, that's my last slide. I'm probably not going to finish, but this is just an example of defining a function. So if in Python you wanted to write this fancy function that says add 3, takes x, add 3, returns x plus 3. Okay, you do it like this. In PostScript you write it like this, and it's kind of similar. Def is there, but def is at the end, so you kind of read it backwards. Def takes 2 arguments, which is a name and a block of code, which is in brackets. So def says assign to the name add 3 this block of code, and it says 3 add. And when you call it like this, which is that postfix notation again, 10 add 3. So it says add 3 to 10 equals, does a pop off the stack and print. So you could run it from the command line like this. And there you go.
So, title of this, I believe you can all read that, but is true true? A mini venture into Python and Ruby truth value testing. So I work a lot with people who are beginning programmers. I'm actually working with one right now in the Chippy mentoring program, and a few people that I've met who want to make the change to Python have actually come from a Ruby background. So I myself made the transition from Ruby into Python, and I kind of remember one of the early days of using Python, I was sitting there and I was like, what is going on? Why is this not evaluating and behaving the way that I anticipate? So really small, right? Really small nuance. So in Ruby land, I can say, if an empty array puts a message, it's going to say, hey, I can't do that. But in Python land, I can say, hey, if empty list print something, it's actually going to print something. So this was a conversation I actually just had recently with my mentee. Confusion. So, hi, my name's Lorena Mesa, and I want to point out to you some of the feelings of existential angst that I have felt as a programmer moving from Ruby to Python. And really the question is, to be or not to be? That is the question. Okay, so Ruby and Python. All right, so apparently there's a lot of angst or ire between Ruby and Python. Granted, this seems to be a one-way relationship, and it's mostly from Python developers I know. So this is what I know when I think of Python and I think of Ruby. They're both dynamic languages. They have user-friendly syntax. They can be used for web and game development, system admin, etc., etc. So what's the difference? All right, so I know that this was a little touched on, but this was like one of the first things I learned about Python. Someone said, okay, go into your shell and do import this. And I'm like, well, why do I want to do import this? And right away I got this list of like the 10 commandments, except I don't know actually how many lists there are in the Zen of Python. But some things that stuck out right away that I thought were pretty interesting was explicit is better than implicit, and this other one. There should be one and preferably only one obvious way to do it. Okay, so if that is supposed to be the Zen of Python, explicit is better than implicit, there should be one and preferably only one obvious way to do something, what can we say about the philosophy then about Ruby? So I don't know actually how you would say this acronym, but there is more than one way to do it. That has been the defining kind of logic or philosophy I have been told time after time after time when it comes to Ruby. I didn't really know where the origins of that came from, and so finally someone said, well, actually, if you go and look it up, Mats, the creator of Ruby, is heavily influenced by Perl, and Perl has more than one way to do something. So let's review this. Explicit is better than implicit. Ruby's being influenced and saying there's more than one way to do it. Okay, so Python true. So for item in my list, print is true. All of these objects are being treated as true. So you have a string, you have an int, you have lists that you have collections that have entities in them, and they're all being treated as true. What about Ruby? So looking at kind of the same ecosystem here, we have a number, we have lists, we have a hash, we have the actual Boolean itself true, an empty string 0. These are all being treated as true as well. So explicit is better than implicit, right? Okay, so something about Ruby when it comes to truth testing, there's only 2 values that are actually treated as falsy values. That's going to be nil and false. Everything else is going to have implicit value, an implicit truthy value, including 0. This stands in opposition, though, to Python, where you can have empty collections that are treated as falsy as well as 0 itself. So again, back to this driving that point home. So if you're looking at the results when you're treating objects and trying to see its implicit truth or false values, you see that when you ask are two objects equal, like is an empty array equal to true, you get that it's true. Same being said when you are saying is when you have two empty lists and you say are these equal, you're going to be getting that yes, it's true. And then just to reiterate, just kind of the objects that get back and define the ecosystem, you get back these three objects: true class, false class, and nil class. And again, to reiterate how that's being implemented, you can confirm that you get one instance of each of these objects whenever you're working with them. So does that stand in opposition at all to Python? So the big thing here so far is you see that there's kind of this different definition of what can be considered falsy or truthy, but really they're being kind of implemented the same way. You see here that you're restricted to one object that can represent true, false, or nil, and you also can see that the idea of kind of an absence of something still with some small nuances is a little different in Python versus Ruby. So to reiterate on this, again, we can check the idea of things that evaluate true or false. We see that you're limited to just having one object that will represent true, false, or none. And the differences here would be you get an object type bool that represents true or false, or you get an object none type. So again, we still kind of have this ecosystem where you're restricted to having finite objects that can represent true, false, or nil or none. Just there's a little bit of a different treatment when it comes to collections.
1 minute.
Awesome. So I think the big takeaway I found when explaining why does Python have a little bit of a different treatment of what false looks like is really you can look at the PEP standards here. This idea of what a bool is actually a subclass of int. And the idea here of it being a subclass of int is actually you're just overwriting the values of str and repr, and rather than representing them as 1 and 0, you're rewriting it to represent as true and false. So while this may seem, this can have some odd consequences, in explaining this with my mentee, one of the things she thought that was interesting is you can do true plus 1, 2, 3, you get a mathematical operation as a result. If you try to do that same logic in Ruby, that's not the case, because you're actually using an object that's not a subclass of an integer or a number. So again, in objects that you write and control yourself, you can control this by doing the non-zero and defining that having a return value of 0 or 1. And for objects that again kind of act like an iterable or a collection, very cool. You can define like.
And ultimately build something cool, do a demo, and win prizes. Now, does that sound awesome?
Yeah. Yes, it does.
So we are going to do the hackathon pretty soon. The details are still not finalized. And once we have those finalized, we'll send it out to the list. And so come and hack with us.
Thank you, team. Awesome.
Ready.
All right, we're ready. So, without further ado, so when you're ready, just hold on a second. Are you ready?
Yep.
Okay. Wait a second. I'm gonna cut my timer. All right, go.
Okay. I am going to talk about programming in Conway's Game of Life. Life was first described in 1970 and was an outgrowth of the history of trying to define what you can compute mathematically. So there are many implementations of Life. We just saw one written in Qt's QML. This that I'm showing here is Golly. It's currently the most advanced simulation system for the Game of Life. It's written in C++ and has an API to program it in Python, which unfortunately I'm not going to get to. So in Life, we have a grid, and each cell in the grid can either be alive or dead. A cell comes to life when 3 cells nearby are alive. So now, if there is only 1 cell next to it, only 1 cell alive, or 2 cells, those cells will die of loneliness in the next generation. 4 through 8 neighbor cells, then the cell will die of overcrowding. So when programming life, the idea is you set up the initial conditions and you run it and see what happens when these simple rules are applied generation after generation. So here we have a random pattern, and when you run a random pattern, you get something that looks rather random, and you eventually get a number of these things, which, if you notice, they're called gliders. They repeat, but after 4 generations, they're back to the same shape, but up 1 and over 1. So when this was found, Dr. Conway offered, when this was first being investigated, Dr. Conway offered a $50 prize to the first person who could prove whether there was any pattern which could grow forever. And the proof was provided with this. This is the first glider gun. And as it runs, it continuously produces gliders. Now, when patterns interact in life, it looks random and unpredictable, but the same starting pattern always produces the same evolution. And this is what allows life to be programmed. Now, for instance, when 2 gliders run into each other, they first make a block, and then the next 2 gliders destroy that block. But if we move one of the glider guns up and to the, just up 1 pixel, now we have gliders that destroy each other. And so if you remove the right glider gun and instead put in a sequence of gliders where every 3rd glider is not there, then as long as this runs, or as long as your gliders continue, you take out every 3rd glider. And so this is a divide by 3 operation. Now, there are patterns which will produce gliders where every 3rd one is missing. But to show you something a little more interesting, this is something that was produced by the people that wrote Golly. They produce gliders in a sequence. And it runs into something called an eater and is gone. So, from the theory of the Turing machine, we know we have to have symbols that interact with each other according to rules. They have to modify the internal state and create output symbols. And in life, these gliders are the symbols, and interacting with the rest of the life grid is both the state of the machine and its output. So, to show you can actually compute something, this is the sieve of Eratosthenes, computing prime numbers, and the sequence of primes will be the ones that pass this spot here. And we have 2, 3, 5, 7, 11, 13. And so thank you. I hope this gives you an appreciation. Oh.
Yeah, you can go for 2 more minutes.
Oh.
7 minutes.
Okay, so the idea is that even without a language, you can do programming. And this is important when we're considering other systems other than computers. So the internal mechanisms of your cell is actually Turing compatible. It can be programmed even though there is no language to program it with.
There's actually controversy starting to stir in like physics as to whether or not this is happening in like Planck scales for everything that's all around us right now.
Yep.
Okay, we got a minute left. You want to use it or ask more questions? We have 50 seconds.
Okay. Yeah, I timed myself to do it under 50. The original inspiration for Go was a paper about self-reproducing systems where they had a very complicated grid and a very complicated structure, and Dr. Conway, who invented life, was trying to simplify this on the basis that any Turing machine is as powerful as any other Turing machine. It doesn't matter how many states you have, how many inputs you have, that you can eventually compute anything with a smaller Turing machine that you can with a larger Turing machine. It just takes more cycles.
Okay. Thank you.
I'm here talking about JavaScript. JavaScript is kind of like the really popular jock in high school that everyone like loves and interacts with, but you don't actually understand why. It's a love child. Switch right up. It's the love child of Self and Scheme. Scheme is a Lisp. If you've written Lisp, it's enriching. Self, I have not really messed around with, but it is probably okay enough. Although the fact that it spawned JavaScript is probably a bit of a tick off that. It was made in 1996, I think. I didn't connect to the internet, so I can't really fact check. It was made by Brendan Eich, who is, he donated Prop 8, so I don't need to slander him any more than that. Or against it. It was made in 2 weeks as a marketing ploy for Netscape because they needed something to interact or fight Java, and yeah, so now we have it everywhere, and it's just incredibly pervasive. It's dynamic like our friend Python. You can just create functions willy-nilly. You can make recursive functions. It has closures like decorators in Python, except with more like lexical scope. I don't know. People bitch about that in Python. I don't really care. It has hoisting. It has a bunch of other stuff. It has notion of safety that I can't describe. It has an incredibly rich type system. You have your object, which encompasses JSON and lists. You have your function, which is technically an object, but in a weird way. You have number, which is floats, ints, everything that you want. You know, if you have 99 point whatever. Anyway. And you have strings, which we all know and love. Like I said, it's object-oriented. If you do this in JavaScript, it will tell you that it is an object. It's prototypical, which means that you don't have the classic inheritance model. So if you see here, there you go. You can create a person, set its argument as a class member, whatever, then define a function on it that gets boiled down to every instance of that type. So if I said JS, or if I had made JS and called it person JavaScript and then did JS sucks, it would print out this function here. And then if I said, new person David sucks, whatever. It has a lot of awesome runtime environments. The browser, all your big ones, your Internet Explorers, your Firefoxes, your Chromes, your Netscapes, RIP.
Opera?
And Opera, yeah, any browser supports it, except for Lynx and the other ones that sysadmins use. There's the server. You have Node.js and IO.js that both run on x86, which it's horrible. The whole event loop bullshit. And if you've ever tried to actually run a JavaScript program on ARM or on Raspberry Pi, don't do it. That's all. So back in the day, JavaScript was pervasive in all browsers, and then jQuery came around and made it even more pervasive. So, that is kind of rough. And then something happened recently. The semantic web, people were making all these front-end frameworks. Backbone came out, everything else. People just kind of went JS crazy. People decided that there was not enough of a way to describe to-do apps, so then to-do.mvc was made, which was great. So now you know what JavaScript framework to use for your to-do app. And it could even be backed by a Python backend or whatever. Probably you should do Node, but anyway, there are hundreds of these made per day. Kind of glossed over that previous slide with V8 and Node. It's on the server now. There's the event loop, whatever. It became prod ready. Any 8th grader could deploy their Node app to npm. You want to like send out some push notifications, and you're sending it to 500 people. You have a memory leak. It just takes down an EC2 medium instance, and then you tell your product manager why are we using Node, and it's cool. So yeah, tests end up not being a big thing of the Node ecosystem, and they decided, you know what, this is wrong. We should create hundreds of these things. And so now, I mean, these existed before Node probably. Again, I didn't really fact check. But you have Mocha, Jasmine, QUnit, which is kind of like JUnit, which goes back to the whole Java roots. We have some offshoot languages which are equally as rich. CoffeeScript, you have TypeScript. You have Dart, which could have implemented bytecode in the browser, and then we would have been in the same place that we are with Python, but unfortunately we didn't get that blessing by Google. Then you have ClojureScript, which Clojure, I don't know, it's Lisp, but again, I guess technically all of these are, well, except Dart, and probably TypeScript. And there are other ones too. For packaging, for the front end, you have require.js, which doesn't actually do any packaging. It just makes sure that you can do something like import and don't shoot me in the foot. That was replaced by Browserify, but they still exist, and there are hundreds of Twitter posts defending both. And then you have NPM in the backend, and Bower and Gulp, and probably other stuff that I'm not remembering. But anyway, so JavaScript, it's a rich platform. Some would say it's a language similar to Python, and that's JavaScript in a nutshell, and why you should be using it. I have 1 minute. Yeah, all right. So that's the talk. But if you guys have questions about JavaScript, I won't answer. Well, I'll answer them, but in complete earnest.
Why do you love JavaScript?
I love JavaScript because every time I've ever had a backend developer position, I've gotten to write JavaScript, and it's just like it's great when you get your CSS and your JavaScript all muddied up with the database, and like when you want to worry about a caching layer and you're just like trying to figure out why Internet Explorer 8 isn't interacting with some click correctly. That's why I love it. Yeah, if anyone has any other questions, I'd gladly talk about JavaScript. But it kind of looks like there aren't any. So.
Hi, I'm Chris. I work at Vocal, a digital agency here in Chicago. I'm here to just talk a little bit about Go and fun times with concurrency. Not quite different than the experience I just had with my laptop. Go has some similarities with Python, or things that I see similar. You can write code in sort of imperative style, or you can actually write it in sort of an object-oriented style. Don't tell Rob Pike that. It's great for writing web servers because you have a lot of requests you need to handle concurrently. Arrays use Python like slicing syntax, so if you need to take different pieces and parts out of arrays and mix and match them, that's quite natural if you use Python. It's easy to iterate over lists and maps, which are sort of similar to, or arrays and maps, which are similar to lists and dictionaries, using the range function. You can return multiple values from any function. It has some kind of built-in package management. So, I mean, Python basically uses pip install things. Go uses get, the go get command. So what the difference is you put all your imports in your files, you set go get, it'll scan your files, look for any imports, and it'll basically try to get them from wherever they're at. Usually like online repos like GitHub or Bitbucket. Also has anonymous functions, which are used quite often in Go. But there are some differences, and the first one that some people might notice right away is that it has a really annoying, my personal opinion, annoying C-like syntax. It's a compiled language; it's not interpreted, so you have to compile your code before you run it. On the upside, it has a very rigid and simple syntax. So like Python, there's usually one way to do a thing. Like for instance, if you want to write any kind of loop, there's only one way to write a loop. Like there's not a while loop, you write a for loop. But because of that rigid syntax, it compiles very quickly, and so you can get almost the same speed as far as, making some changes, building it, running it, testing it. You can get that almost the same speed as you can with Python. It uses packages instead of modules. It uses camel casing instead of underscores to indicate whether something is exported or public. You start with a capital letter. If it has a lowercase letter, it's not exported. That means it can't be accessed outside the package. It also uses a convention of returning errors from functions, a separate error, instead of raising exceptions and handling exceptions. But Go has no GIL, which when you have, for certain kinds of operations where you need to have a lot of things that run concurrently, that can actually be a real benefit. Python has some ways to do concurrency. Async IO is like the most recent. There are basically packages that sort of generate their own runtime loop, event loops, and then run everything within those event loops. But the Go runtime itself has a very efficient and very schedule that just automatically schedules, and you tell it to do, you tell it to do 10 things, and it'll automatically figure out which of those 10 things should be executed at any given time. If it needs to create new threads, it will. If it can take advantage of multiple cores, it will do it automatically. But that efficiency, it's so good that it doesn't even guarantee that all your operations will even execute. It schedules them, and if your program ends before something finishes running, then it just doesn't happen. So the main idea that Go uses is called Go routines. Everything in Go is a Go routine. So even your main, if you remember your C, days it all, any of your main function, it's basically a Go routine. If from main you can call another function, give it the keyword Go, it'll create a separate Go routine and execute, and the schedule will execute that concurrently with main. In this example here is really, really ridiculous, but you can see within main, I have a string, I send that string to the do stuff function using the keyword Go. It'll execute separately. One thing to kind of pay attention here, though, is that right after I tell, basically I'm instructing the Go runtime, okay, take this other function and run it concurrently with main, but right after that, main ends. And so it'll end, and your Go routine might not have finished. So Go uses basically blocking operations to decide, when to schedule things to run. If something happening in one Go routine starts blocking, it'll start working on another Go routine. And this happens, obviously millions of times a second. One real handy thing you can do is you can defer execution using the defer keyword, and whatever you tell it to do will basically happen as soon as the function comes to the end. All the instructions have stopped running, and it's about to return. It'll take anything that you told it to defer and run it right before then. I'm going to move even faster. You can do wait groups, which is the super most basic, easy way to handle multiple Go routines. Basically, every time you call add on you use this wait group thing, you call add on it, you increment it, then you fire off some functions. Inside those Go routines, you tell it that it's done, and basically it'll just start de-incrementing. And then after you've fired everything off, you just tell it to wait, and it'll just wait until all the decrements have happened. The other big thing that Go has built in is channels. So this is basically a way to just communicate from Go routine to Go routine. You can send information on the channel, and then another Go routine can wait until that information comes through on the channel and react to it. So this is a really kind of basic sample here, but this pinger function is sending the word ping along a channel. This printer waits until it gets a string, and then it prints the string out. Thank you, everyone, for coming to Chippy tonight. My name's Jason, and who here has been programming for more than 5 years? Raise your hand. Who here has been programming for less than 5 years? Raise your hand. Who here has been programming for 1 year? Who here has just programmed tonight? Raise your hand. All right, a round of applause for all of our presenters. You know, I think sometimes when we program, we think about very high-level things. There's really basic things that we can think about. And a lot of that's functions. A lot of that's manipulating data. And a lot of that's what we do on day-to-day as programmers. Who here knows what this terminal prompt is? Shout it out! What makes IPython so great? Colorful! What was that? Tab completion.
Charts.
What?
Charts.
That's matplotlib. But notebook integration makes it awesome, right? So we got tab completion. We kind of have charts. What's something else that IPython brings us? Pretty prints, awesome. What if I do...
Question mark.
So what if I do this? What is this going to do? Documentation. Who spends a lot of their day reading documentation? I do. I do probably about 3 things on a while loop all day. I read documentation. I type a couple letters. That too. I type a couple letters. I hit tab. I hit, dot. I look through things. And I write functions. And so IPython has that. Now, I really like finance. And I come from a world of spreadsheets. I cut my teeth kind of programming on spreadsheets. One of the things that I like about them is a very simple kind of programming model. One of the things that we do when we program are very simple things, very basic things. We add 2 numbers together. We multiply 2 numbers together. What?
The math doesn't add up here.
Math doesn't add up? So we take a bill. Well, we'll see if it doesn't add up. How much did you pay for Chippy tonight? All right, and then we can multiply that by another number, right? When we program, we do real simple things. We add numbers together. We could take 0 plus. Here, we'll do this. We do simple things such as we add 2 numbers together and we get a value, or often we get an error. And we get things out. We manipulate things. But spreadsheets represent an awesome model for programming. It represents the IPython model. It's what helped me work. What IPython helped me translate from Excel into programming and then into Python. Part of it was that it was visual. If you're learning to program, it helps that you can see the data that you're working with, right? This is Google Spreadsheets, right? Everybody in the world has access to Google Spreadsheets if you have access to a relatively fast internet connection. It means that this programming model is more powerful than Python because it's available to more people in the world than has ever been possible before. It's awesome because it's visual. If you want to teach your grandmother the basics of programming, computing on data, taking data in, transforming it, and doing something out, this is an awesome model. You could take a simple string, hello, and then in Python you can do a string.upper. But you know what? This has that too, upper. And what do we get here? We get very similar things to what we have in IPython, right? We get documentation. What happens if I hit tab? We get tab completion. It tells us what we're going to do, right? It gives us examples. Google Spreadsheets is awesome because it shows us what we should put in, what we should get out, and it even tells us how to write documentation. I listed a few things I did earlier at my day job. What's one of the things I didn't mention? Writing documentation, yes, because Python is very readable. So you can do simple things like that. You can calculate very simple statistics. Who wants
Who's ever played a game with random dice? Who's gone to Vegas and played craps before? There should be way more hands than that. But if you want to simulate random numbers, there's simple functions in here to do that. Ran between, right? 1 and 6 should give you random numbers, right? Now, what if you want multiple random numbers? You just drag the cell down. How easy is it to compute that? But what is kind of lost in maybe the simplicity of the user interface, what's lost in the simplicity of navigating the tools, is what you're doing to the data, how you're computing it, the process that you're taking, right? I can take this data and I can apply a simple sum to it. AutoSum is probably the most used function in the history of the world. Why? Because you can just hit sum and it just works. But people understand that model. And it doesn't take a lot of computer science background to understand how it works, but it takes conceptual thinking that we need to bridge between the world that we live in and the computers that manipulate our data. So what we do at our day jobs is fun. I love programming in Python. There's a lot of ways to think about computation. And I think spreadsheets is an awesome model for that. Thank you.
Stop talking, because I'm going to turn off your mic, and I'm going to wrestle. Oh. Jerry's going to wrestle you. He's much bigger. In a kind and soft manner, of course. And so the rule is there needs to be at least one Python reference. And you can just say the word. You can say, like, I like Monty Python Flying Circus, like a Brian. You can say, just say that, but you have to at least make one reference throughout the talk. Because we are a Python user group. So, there's going to be a break between sessions, and we won't start until someone gets ready. I'm going to put a timer on the desk. So we're going to go in the order that people checked in tonight. So being on time always helps.
My name is James Swain. I work at Braintree with Adam Forsyth. And tonight, tonight I'm going to talk about OCaml. So the kind of phrase I think best encapsulates OCaml is that it's multi-paradigm. You can write code using a lot of different programming styles, some of which are familiar to you and others which may or may not be familiar to you. Kind of the predominant paradigm that you see in OCaml code is the functional paradigm. Some of you are maybe familiar with this, some of you may not. So this code sample here, this is just like an implementation of the map function, which you probably have seen. If not, it just takes a function and a list as input, and then returns to you a list that contains all the elements of the input list with the function applied to each one. So here you can see a couple of things that are sort of functional in nature. You can write recursive functions. You can do pattern matching, which is like a destructive sort of case dispatch on values. So here, in match, the base case is, do we get the empty list? So then in that case, we return the empty list. Otherwise, if the list is an element, cons onto a tail list, then we return the result of applying x to f, cons onto map of the rest of the list. And then also here is another kind of, can everybody hear me okay? Good, okay. Another example, or kind of example here, we're going to use the map function, and we're going to create a list of the numbers 1, 2, 3, 4, and we're going to pipe it into map. And the map, that expression there is a partial application of map, where the function argument is adding a function that adds 1 to any number. And so here we're actually partially applying plus. And so that will give us the list 2, 3, 4, 5. Then we pipe that into filter, which we only return all the even elements in the list, which gives us 2 and 4. Also, you can do like actual object-oriented programming in OCaml. It's not as commonly used, but you have all the facilities that you would see in any language that has more emphasis on this sort of thing, like a Python or Ruby. And here, this is just like a basic stack class. Notice that also you can have like fields and methods, but if you want to do any kind of mutation, you have to be explicit about it. In OCaml, everything is immutable by default. And then also the thing that sort of comes along with that is the imperative programming style, where here we're actually using the stack class that we just saw in the last example, and we're actually writing just a basic for loop that you'd see in any language, C or whatever. And here we're just going to push the numbers from 0 to 5 onto the stack, and then pop the last one, and we get 5 back. So quickly, since we're short on time, features that 4 minutes, good, awesome. 4 minutes left, or
4 minutes left.
Okay, cool. So some things that we've already seen, some things we haven't. OCaml supports first-class functions, higher-order functions like a map or whatever. Lexical closures, where you can create a function sort of inline that implicitly captures all the bindings that were outside the scope of the body of the function. It has static type checking with type inference. So you notice that in all of these examples, we never have any sort of type annotations anywhere. The compiler just kind of figures out what the type should be. And in some cases, you may need to use type annotations to kind of help the compiler understand what you're doing. Also pattern matching, which we saw. First-class higher-order modules, which is like a really cool feature that you don't see in a lot of other languages. You can write modules in OCaml that take other modules as parameters. You can write functions that build up modules using arbitrary values, functions that take them as arguments. You can do really cool stuff with that. There is a macro system that's not quite as refined as like a Scheme or Racket or whatever. It's portable, it's cross-platform, just like Python. And it's actually very fast compared to like other languages in this family like Haskell or even Scala. It's got pretty good performance characteristics. It has some of the nice conveniences that you would see in other languages. It has a package manager. It's very actively contributed to. It's very easy to use. So this is just a screenshot that I took from the OPAM website, which is the OCaml package manager. It's pretty active, as you can see. There are 887 packages there now. This past week, there were like 27,000 something package downloads. So it's got a pretty active community. Notable users. This language is actually used like in real life, which is kind of cool. So James Street Capital is like the biggest, probably commercial user of OCaml in the world. They do like quantitative trading, high frequency trading. They're based in New York City. They write their whole stack. Their whole stack is in OCaml. They have actually like rewritten the OCaml standard library and like improved it. So they've rolled like their own sort of like OCaml ecosystem. They have a lot of nice build tools and stuff. So it's pretty neat. Bloomberg apparently uses it for some of their like pricing tools that I know very little about. Mirage OS or Unikernel, which is
Brian said, hope to continue the partnership and do some more stuff. And we're super excited about tonight and hope everyone has a great time.
Thanks. Joe. So Imaginary Landscape, long legacy in Chippy and in Python community. Name a few when you give your intro of people who can interview. Yeah.
I'm Joe Jasinski.
I'm here for the Go talk.
You got it.
I'm Joe Jasinski. I'm with Imaginary Landscape. We're a Django Python web developer here in Chicago. I've been doing it since 2006 and Python since about 99. Sure. We've had people come through us like Ian Dicking and Chris Weber and a bunch of others, Tomas. So we really love Django, and we work with a lot of cool web dev stuff. If you want to learn a little bit more about us, I'd be glad to talk about it. So come see me, and we're happy to sponsor help sponsor Chippy tonight. So
awesome. So I don't have to GitHub tonight, but thank you to them too. So we're gonna get this started. And one thing is if you are not from the Python community, we have we've killed trees for this. So Carl has a lot of dead trees that have been mashed and tattooed with ink. So if you want to learn about how awesome Python is, I'm going to leave this right up here. So during one of our breaks, you can look at it, and he has more that he can give you, so you can put it on your fridge, if you so desire. All right, so we do have talks lined up tonight, and I'm going to tell you how this works. We're getting 7 minutes. Yes, I've increased it by 2 minutes per talk.
Thank you.
Because a couple of people, I don't know what happened, bad stuff happened, and they're not going to be able to make it. But there's plenty here. So we have 7 minutes. It is going to be timed. At the end of 7 minutes, you must stop talking, and you will stop. So sponsorships tonight.
Well, thank you to Computer Futures.
Wait a second. We're going to come up and say something. So, wait a second.
All right.
We have 3 sponsorships tonight. We have Computer Futures, who are going to come up and say something in a moment. We have GitHub. Everybody, I don't know who they are. And we have Imaginary Landscape, which is an old school web weaving company. And we have someone that's Joe's gonna speak a little bit about that. So first, making this possible tonight, huge turnout. Give a warm thank you and come on up here, Computer Futures, please. Thanks, guys. And we're doing more with these guys, more and more, so we deem them not douchey.
But don't speak too soon.
No, give me that.
Thanks, Brian. I'll keep it short, but hey guys, I'm Charlie, and this is Tom. We're with Computer Futures. Thanks so much for allowing us to to host the event and sponsor and all that. Just a bit of background on who we are. Computer Futures is a recruiting and staffing firm, so we focus on the IT space. The reason why we wanted to partner with people can hear me. The reason why we wanted to partner with Chippy is because we have specific teams of people that focus specifically on the Python space. We're really bought into Python. We think it's an awesome language, and we think it's only going to be kind of going up from here. And we think Chippy does a lot of really cool stuff. So we have teams that focus on Python within the finance space, and that brand's called Huxley. That was we worked with people like Jerry to help him get his job at Bank of America, and then we have a brand called Computer Futures, which focuses on the non-finance space. So yeah, we're super excited to be partnered with Chippy, and like